This is screencast number 2 for Unit 4, Lesson 1. I'm on page 178. How is velocity described? Okay, speed describes how fast an object travels in a given period of time, and another way to describe the motion of an object is its velocity. The velocity of an object is its speed combined with the direction of motion. So speed and velocity are related, but velocity is a little more specific. It also gives direction. Velocity is speed and direction. I'm at the red heading. You sometimes see the terms speed and velocity used interchangeably. This is not correct usage in science, though. Objects moving at the same speed can have different velocities. A car traveling west at 20 kilometers per hour has the same speed as a car traveling east at 20 kilometers per hour, but the two cars have different velocities because the direction part of their velocity is different. So speed and velocity are related, but they are not the same thing. You do calculate velocity the same way you calculate speed, but again, because velocity has a direction with it, it's not exactly the same thing as speed. Now I'm on page 179. What is a vector quantity? Well, a vector quantity is any physical quantity that has both a size and a direction. Velocity is a vector quantity. Why is it a vector quantity? Because you have to specify a direction in order to have velocity. So anything that has to have a direction given with it or implied with it is a vector quantity. There are some things up at the top corner that I've also listed as vector quantities. For example, things that need a direction in order for them to be fully described. Velocity is one. Displacement is another one. We actually talked about displacement a few pages ago, because displacement is how far away are you from where you started. It's basically a straight line distance from where you started to where you ended up, and you need to specify a direction in order to fully describe your displacement. So it's a vector quantity. Acceleration is also a vector quantity. Force is a vector quantity. Momentum is a vector quantity, and so is weight. All right, so those are just some examples. But you just need to understand that a vector quantity is something that has to have direction in order to be completely described. Okay, so back to the red heading where it says velocity is a vector quantity. Okay, vector quantities we're usually going to show on diagrams with arrows, and the bigger the arrow, the larger the quantity. And the arrow is going to point in the direction that vector quantity moves in or is directed towards or oriented towards. For instance, if you had a car that was moving towards the right, then you would draw an arrow representing the car's velocity pointed to the right. And if it was a large velocity, you would make the arrow long, and if it was a small velocity, you would make the arrow short. Average velocity is displacement over time. Now, again, you're going to see that we don't really distinguish very well when we write our formulas, but if you're really going to be picky, average velocity is really displacement over time. Average velocity is calculated as the total displacement over the total time elapsed. But again, you're going to wind up with a formula that looks a whole lot like the formula that we started with when we just did speed. Just keep in mind, the really important thing to keep in mind is that velocity is a vector quantity, and vector quantities have to have a direction with it. So if I say 55 miles an hour, that's a speed. But if I say 55 miles an hour east, that is a velocity. All right, I'd like you to look at the bottom of page 178 and 179. Let's look at page 178 first. On number 13, under Visualize It, it says identify the velocities of the fastest ship and the slowest ship shown below. The fastest one, I'm going to look for the longest arrow, but also beside the arrow it does tell me its velocity. So the fastest one is the one that's going 8 kilometers per hour south. The slowest boat is the one that is headed 1 kilometer per hour east in Galveston Bay. And again, that little arrow is a lot shorter than the arrow that represented the boat going 8 kilometers per hour. Okay, look at page 179. Do the math. A ship is traveling south, assuming that the ship has a constant velocity during each segment of the cruise. Make a distance versus time graph using these values for total distance traveled. All right, I've already plotted everything for you. You notice that from time equals 4 hours to time equals 6 hours, your distance remained 9, meaning that the ship must have been docked or it wasn't going anywhere. Okay, so the velocity for that ship during that time would have been 0. All right, but I've plotted my graph. I used time as the x value. I used distance as the y value. And remember, velocity is calculated the same way that you calculate speed. It's just velocity needs a direction. So we're going to calculate velocity by saying distance divided by time. On 16, it says use your graph to determine the velocity of the ship during the 1 hour period from 2 hours to 3 hours. And to help you guys sort of visualize that, I shaded it green. Okay, the change in distance during that time period, it ended at 7 kilometers. It had started that time period at 5 kilometers. The change in time, it ended at the 3 hour mark and it started at the 2 hour mark. So that's a change in 1 hour. So the change in distance was 2 kilometers and the change in time was 1 hour. So the average velocity for that particular part of the graph was 2 kilometers per hour. There's also another one that's shaded kind of pink, and that is a different part of the graph. That was from time equals 6 hours to time equals 8 hours. So that's a 2 hour time frame. And you'll notice if you read the graph carefully that it covered 3 kilometers in that time period. So 3 divided by 2, during that time period, the ship was not cruising quite as fast because it's 3 divided by 2 is only 1.5. So it wasn't going quite as fast as the little green time interval. Okay, but you can figure that stuff up by looking carefully at the graph, figuring out what was your beginning distance, what was your ending distance, your beginning time and your ending time, and basically doing the same thing that you're going to be doing in math, which is calculating slope or rise over run or whatever you want to call it. Okay, but you can get your distance and time values off of a graph just like I did. I've now turned the page to page 180, and I'm at the blue heading that says, how is acceleration described? Well, this is a new word, so let's talk about acceleration. Acceleration is a measure of how quickly velocity changes. Acceleration describes the change in velocity, which is in meters per second, over time, which is in seconds. Because if you look carefully, velocity is in meters per second, so there's one time unit, and then it's divided by another time unit, seconds. That's why acceleration is measured in meters per second, or they'll just say meters per second squared, meaning that there are 2 time units and 1 distance unit. Okay? Acceleration is a change in speed, a change in direction, or both. Acceleration is the measure of the change in velocity. Acceleration occurs when there's a change in speed, a change in direction, or both. And I put down to the side, and you need to write it down as well, acceleration happens anytime you speed up, slow down, or change direction. I've also put the formula for acceleration. Above that, acceleration equals the change in velocity. Remember that little triangle means the words change in. Acceleration is change in velocity divided by change in time. And acceleration's units are meters per second divided by seconds. That's how you get the meters per second squared. Okay, I also pointed out that acceleration is something that you can feel. For instance, if you get in a car and you're driving down the road, and you're in the passenger seat minding your own business, and somebody slams on the brakes, you feel that because you wind up slamming into the seat belt, okay, and you are very aware of the fact that the car has slowed down, okay? That is one form of acceleration, slowing down. If you are driving in a car and you're sitting in the passenger seat minding your own business, not paying attention, and they whip around a curve, then all of a sudden you're going to be thrown either towards the passenger side window or over towards the driver. You're going to lurch one way or the other. And again, it's because you're accelerating. Acceleration is something you can feel. If you are in a car and somebody just guns it, hits the accelerator, floors it, then you're pushed back really hard into your seat. You can feel acceleration. Okay? Acceleration, one more time, is when something speeds up, slows down, or changes direction. Acceleration is a change in velocity. Okay? And it's a change in speed or direction because remember, velocity involves both speed and direction. All right, let's look at number 17. Label the arrows in the soccer game diagram to indicate changes. The defender turns as he moves into place. He is turning, that is an acceleration because his D direction is changing. The ball slows slightly due to friction. Okay, the fact that the ball is slowing is a change in speed. So I put an S. The goalie turns and begins to run toward the ball. She both changed her direction by turning and changed her speed by running towards the ball. So that was a B for both. Okay, everything on page 181 you can skip. And that's probably going to bring us to the end of this screencast.